Hey everybody, Professor Brown here, and in this video I'm going to cover NMR spectroscopy, which is a technique that we use to further characterize molecules in the organic chemistry laboratory. We'll describe what the spectrum can tell you and look at some examples throughout this set of notes. So if you will, follow along with me and we'll learn all about it. Here we have a look in these pictures of what a sample tube looks like for an NMR spectrometer. You can see the size of the tube relative to the person's hand, with the liquid down there in the bottom containing the sample. So the liquid is actually a solvent, and the sample molecule we're studying with this particular run would be dissolved in that solvent. And then I really like to include this picture. This is a picture of one of the more advanced NMR spectrometers in the world right now, and you can see the size of it. So this tiny little sample tube in relation to this giant looking instrument slides down. You have to climb the steps that you see here and put the tube in the top of the instrument, and then the tube slides down into the instrument and is analyzed using this technique. The reason for the size of the instrument is because, as we'll explain in a minute, you need superconducting magnets for the theory behind the technique to work. And so these are large cooling chambers. The actual instrumentation is just some electronics inside. The big outside structure you see there is a large cooling chamber that contains liquid nitrogen and liquid helium, and that's what would be found in these shiny tanks down here that are feeding this giant cooling jacket, is what you're looking at there. So just a kind of a look at what a real NMR looks like, because our lab does not have one, certainly not one of that magnitude. So a way to get a look at one, what they really look like here. So here on this slide, we're going to start talking a little bit about the background behind NMR spectroscopy and talk about the theory and how it works, so we can make sense of the signals and what it tells us about the molecules in just a moment. I've got a picture there up top of a more reasonably sized, a more kind of commonly sized NMR spectrometer. I've seen a number of these throughout different university labs and worked with a number of these, so just kind of speaking to the more general use type spectrometer, this is kind of more what they look like. And so like I said, a little bit of background about NMR spectroscopy. If you may somewhat have paid attention, if you paid attention really good, along the way in your chemical education, we've talked about a property that some subatomic particles have called spin. You may have heard us talk about it, especially in relation to electrons, because when electrons pair up in an atomic orbital, they have to have opposite spin. They can't occupy the same atomic orbital unless they have opposite spins. And it turns out not just electrons have spin, protons have spin as well. And when nuclei have odd numbers of particles, and you can think of like the hydrogen nucleus only has one proton, so that's an odd number of particles. It's one. Then this spin imparts a magnetic field, and this only happens when you have an odd number of subatomic particles in the nucleus. There's an overall magnetic field generated by the spin of that subatomic particle. And the instruments, the NMR spectrometers, we put these molecules down inside of these spectrometers, and we use these spectrometers to subject them to an outside magnetic field called the applied field. And because the nuclei of all of the hydrogens on these organic molecules that we put into the machine are behaving as tiny magnets because of their spin, they line up with that magnetic field. So we put the sample down in the middle of this superconducting magnet that you see here. So we put the sample down in the middle, much like I was just explaining. There's a tube that drops down in the middle of this machine. And this instrument, which is a big, giant superconducting electromagnet, we switch it on and it generates this giant magnetic field. In fact, when you go in these rooms, you have to be really careful not to take your bank cards and a lot of it used to be you didn't want to take your phones and things near these instruments because they generated such large magnetic fields. So it generates this very strong magnetic field, and the nuclei all line up with that magnetic field. Some of them, it's important to note, some of them line up with the magnetic field and some of them line up against the magnetic field. And one of those is a little bit higher energy situation and one of them is a little bit lower energy situation. And the difference between those two is really important for NMR spectroscopy. So like I said, our study will focus on H1 or 1H NMR spectroscopy, which focuses on the hydrogens in an organic molecule. We do have other forms of spectroscopy. Of course, regular carbon-12 has an even number of nucleons or subatomic particles in the nucleus, but so we can't do NMR spectroscopy on carbon-12. But if we remember, there are some carbon-13 atoms randomly throughout our molecules in the universe. There is carbon-13 spectroscopy, NMR spectroscopy, and I do have a different set of notes on that to come later on. But for this set of notes, we're going to focus on 1H NMR spectroscopy. So as I was saying in the previous slide, when we switch these instruments on, we generate this large magnetic field, and our hydrogen atoms in our molecules line up with that magnetic field. And some of them line up opposed to the magnetic field, and some of them line up directly in line to the magnetic field. The ones that are opposed to the magnetic field are at a higher energy state than the ones that are directly in line with the magnetic field. And furthermore, we can cause them to flip between those states by exposing them to the correct amount of energy. And when we do so, those nuclei will absorb that energy and flip between the low energy state and the high energy state. It turns out the energy needed, the energy range needed to cause that flip is just in the radio frequency range. So we have to have a large magnetic field, but the energy that we hit these molecules with are at radio frequency. So in the grand scheme of things, a rather low energy frequency. We're constantly bathed in radio frequency radiation at all times. So we shoot some, we align these molecules in a very strong magnetic field, and then we pulse radio frequency radiation at them. We see which specific frequencies of the band that we send through the molecules are absorbed, and the specific bands, those signals, the understanding of which bands are absorbed gives us information about the particular hydrogens in this case. Because we're studying the hydrogens, it gives us information about the different hydrogens in our molecule. So we'll investigate what that means here shortly. We can see the animation is not turned on there. So you can see, so when the atoms are oriented in their magnetic field, we shoot the radio frequency radiation at them. They tip over and absorb that energy, and the absorption is measured by some detector in the instrument. So again, we are testing we are seeing which frequencies are absorbed by our instrumentation, and we can process that as information about the hydrogens present in our molecule. All right, so on this slide we have an example of what an NMR spectrum looks like. Uh, the energy gap that we were just talking about on the previous slide, it's determined by a nuclei's local electronic environment. We'll investigate what we mean by that in just a moment, but it's important to know that nuclei with identical environments will give identical signals. Nuclei in different environments will give different signals, and of course that's what gives us the different signals that we can evaluate to get the information from the spectra, kind of like we're looking at here. The things we're going to look at are the number of different signals tells me how many different chemically groups of protons there are in an NMR spectra. The chemical shift, basically where the signal falls on the graph, will tell me the proximity to other electronegative atoms and other deshielding effects in a molecule. The integration, the area underneath each of these signals for you calculus lovers, tells me the relative number of protons of that particular signal. And the multiplicity, the individual jaggedness you see of these signals, tells me something about the neighbors of each of the protons. So going back through those, the number, each signal, when you're looking at this graph here, each signal is one group of these peaks that you see. So there are three different signals in this molecule. So I know that there are three different groups of chemically equivalent protons in this molecule. And again, we'll investigate what chemically equivalent means in just a moment. I know I can determine how close they are to different electronegative species such as oxygen or bromine by how far these signals fall up or down the graph. I can determine the integration, which luckily is done, usually done electronically for us these days, and that will tell me how many relative protons we're talking about in each group. So remember, I've got three different groups of protons here, and then I can figure out how many protons each group contains by determining the area underneath those peaks. And then I'll talk about finally what we mean by neighbors at the end of the notes here. So here we can see how we get the number of signals on an NMR spectra. The number of different signals is determined by the number of different groups of chemically equivalent protons in a molecule. Chemically equivalent protons are ones that can be interchanged through a symmetry operation. So that is a little bit, usually it's kind of a little bit more complex than it sounds. We can talk about in this picture here what chemically equivalent protons are, and it probably will give you a better picture. So chemically equivalent protons are protons that share a chemical environment. So in the top molecule here, all four of these protons here and here would be considered chemically equivalent. They could all be interchanged with one another and you would never know the difference. And the same would go for the 6 protons here and here. Those are all chemically equivalent. So on an NMR spectra of this molecule, I would expect to see only 2 peaks, and those 2 peaks one peak would represent the 4 protons in the middle, and the other peak would represent the 6 protons on the outsides of the molecule. On this next example here, this ketone that we have in the middle, we have 3 equivalent protons right here. Exchanging any one of those with the other, you couldn't tell the difference. And these 2 are equivalent with each other, and these 3 protons are equivalent right here. So I would expect 3 signals from this molecule for the identified groups. On the next molecule, these 2 protons are chemically equivalent. These 2 protons are chemically equivalent, and these 3 hydrogens are chemically equivalent. So there would be 3 signals in the spectra of that molecule. And the next one, I've got this one to intentionally be a little bit tricky. Even with the oxygen molecule in the middle there, these four, because of the symmetry of this molecule, these four hydrogens here are chemically equivalent to one another, and the six hydrogens on either end of the molecule would be all chemically equivalent with each other as well, and so you would only expect two signals from this particular structure. And in the last example here, we would see the following signals. So these three protons are chemically equivalent to one another. These three protons are chemically equivalent to one another. So we have two different signals there. Now, this CH2 group in the middle, because of the chirality of the carbon in this position here, and it doesn't really matter if it's right adjacent to this position or not, just because of chirality present in the molecule, we no longer would say that these two hydrogens are chemically equivalent. They share different conformations. If you think about the Newman projection of each of those hydrogens, they share different conformations. They would never have the exact same lineup of the methyl group and the bromine and that particular proton. So they are not chemically equivalent, and so you're going to get one signal for this hydrogen and then one signal for this hydrogen. So you're going to get four total signals for that molecule. Actually five, because you have an extra hydrogen here that also is not chemically equivalent to any others. So to summarize, you're going to get five different signals from that molecule, and the CH2 hydrogens there in the middle are not chemically equivalent due to the chirality of the carbon present there. So you can kind of see from my examples here, hopefully, what chemical equivalent protons are and are not. And you see from the easy tips down there some ways that you can always tell what is and is not equivalent. Protons and methyl groups are always equivalent to one another. CH2 protons, as we've seen, most of the time they are equivalent to one another, but when there's a chiral center in the molecule, they are not. So watch out for interchangeable CH3 and CH2 groups like we see here and here, in this case, and these cases, when you have a high symmetry molecule, because in that molecule, all of those protons are chemically equivalent, and you only see two signals. So watch out for those types of cases. So here on this slide, we have some more examples of determining how many NMR signals we would expect from these molecules. And so if we're considering the hydrogens that we can't see, actually there's only one there, so we have a couple of hydrogens here, of course, some hydrogens here, one hydrogen there, and we have three here and three here. So all four of the hydrogens here and here, they're all directly adjacent to one methyl group. They're all two groups away from another methyl group. So all four of those are going to be equivalent and give you one signal. The two CH3 groups on either end are also equivalent to one another, so each of those are going to give you just one signal together as well. So we'll have two total signals for those hydrogens on that molecule. On this molecule, these hydrogens are all going to be dissimilar, and they're all different lengths away from different groups. For instance, this one here, this hydrogen here is one sigma bond away from a methyl group, or two sigma bonds away from a methyl group, and three sigma bonds away from a chlorine, where they're all in different chemical environments. So you would expect four signals from those hydrogens, and then you have a methyl group here. That group of three hydrogens would all be chemically equivalent, so you would expect a fifth signal there. So you would get five signals from this molecule. In the next one here, you have a CH3 group in this position. That would be one signal. You have two hydrogens here, they would be chemically equivalent for two signals. Two hydrogens there, again chemically equivalent for two signals, or one signal. Another pair there, that would be chemically equivalent. One here and one and two more here. So this would be one signal, two signals, three signals, four signals, five signals, six signals total for that molecule. Six. In the next molecule, we would have a hydrogen here and here, and a hydrogen here. These two here would be equivalent to one another. These two here are not equivalent to anything else, so three total signals from that molecule. In the next group, we have some CH3s. These would all be equivalent to one another. These two would be equivalent to one another, and these two would be equivalent to one another. So we would have three total signals from that molecule. In the next example, we have a CH3 group here, a CH2 group here, a CH2 group here, and a CH3 group there. We also have a hydrogen there hiding out with the bromine, and each of the CH2s, because of the chirality of the molecule, each of the CH2s is going to give us two signals. So we are going to expect a total of 1, 2, 3, 4, 5, 6, 7 signals from that molecule. So you can get an idea here of how many signals you would expect depending on whether or not different hydrogens in a molecule are chemically equivalent to one another or not. So now I'm going to start with an example of an NMR spectra of a molecule and show you what different signals may look like based on the protons that we see. The program that I have behind me is nmrium.com, and this is a NMR simulator that will run NMR spectra for any molecule that you draw. You go down here to chemical structures and open it up and click the plus sign, and you get a molecule drawer. So I'm going to start with something kind of simple. I'll start with 2-butanone, which will give us a good structure to evaluate different NMR peaks. I'll click save, and we can use this button here that says predict spectra, and it'll give us some options, and I like to run somewhere between 300 and 500 megahertz. Going up to 1000 or 1.2 means we're running the best instruments on planet Earth, so maybe that's a little unfeasible. Maybe 300 or 400 is a little bit more reasonable for a spectrum we might be able to run. We're only going to select the 1H NMR spectra, and you have to select I confirm. Leave everything else the same and click predict spectra. It'll do a little bit of work, and there we go. And you can see it's got some different highlights there. It will show us what different signals are. So we can see that this first set of peaks here is the signal for the two hydrogens next to the oxygen. The other signal is the methyl group also close to the oxygen, and the other signal, the final signal down here, is the methyl group on the end of the molecule. So three different chemical environments for our hydrogens and three different signals for our hydrogens in that molecule. Kind of demonstrates how the number of signals is correlated to the groups of hydrogen in the molecule. So as you may have seen in that previous demonstration, the location of a signal, what we call the chemical shift, is determined often by how hard it is to flip the proton from the oriented state to the misaligned state. And that all comes down to basically how many electrons or how much electron density is around that atom to shield it from the applied magnetic field. The more shielded a proton is, the less electromagnetic energy will take to flip it back and forth. And so we see it in the less shielded part of the spectrum, which is the spectrum on this side. And for protons that are near electronegative groups, protons that are near oxygens or halogens, or protons in aromatic situations, which protons on benzene rings is how you can think about that right now. They are de-shielded. They have things near them that pull their electrons away, and so they feel a lot of that magnetic field that's being applied, and it requires a lot of energy to flip them between the two states, and those would be found in this part of the NMR spectra. So we'll take a look at how we can predict some of those on the next couple of slides and how we can use it to understand the structure of the molecule. Here you see how the chemical shift is calculated and why we use chemical shift as the reporting unit for NMR spectra. So as you can see, the shift is reported in this lowercase delta unit that we call chemical shift, and the lowercase delta stands for parts per million. The way it's calculated is every NMR run has a standard put into it, and usually that standard is trimethylsilane, which you can see the structure of over here in this bond line structure here behind me. So it's got 3 methyl groups, actually got 4 methyl groups bonded to a silicon atom. And what that does is that allows those groups of hydrogen are very balanced, and they are very shielded from the magnetic field. And so it only takes a little bit of energy to flip them from their aligned state to the unaligned state. And that signal always appears very far upfield in the NMR spectra. And then every other hydrogen is compared to that. However much energy is, or whatever frequency energy is required to flip those protons, is subtracted from the frequency that's required to flip any other proton. And that difference is divided by the operating frequency of the spectrometer overall. And so that may seem, well, why don't we just report the frequency of the proton flip, or the frequency of the energy that sustains the proton flip on the x-axis? And a few reasons for that. Again, frequencies are very high numbers, so we would have a really jumbled x-axis if we did that. But more importantly, doing it this way allows the shift for a particular proton to always be the same over all of the different operating frequencies. So even on an 80 megahertz machine, a proton, say a proton in a CH3 group on a methyl molecule might be 1.2 parts per million on an 80 megahertz machine. It will also be 1.2 parts per million on a 1.2 gigahertz instrument as well. And that's just useful for it to carry across different instruments. We're constantly building higher and higher frequency instruments that require stronger and stronger magnets. We get higher resolution results that we can get more information from when we're using a stronger magnet. So that's why we might be interested in getting a higher frequency instrument. So here we're going to give some examples of how to predict the chemical shift of a set of protons given its proximity to some oxygen structures in a molecule. And we have a table here that tells us the effect of a proton's, or a group of protons, chemical shift due to its proximity. You have to read pretty close in the text to also know that these are the additions to the standard parts per million given here if the proton is on an alpha carbon. There is an effect if it's on a beta carbon, and it's about 1/5 of the figures published here. So we'll take those into account if they are the case. So looking at these structures here, what we want to do is take into account the hydrogen structures that are present in this molecule. So we want to see, can we maybe determine what the chemical shift is on, for instance, this pair of hydrogens that I've drawn in. And the way we do that is we take into account, we see up here in the top right corner that this would be a pair of methylene protons, would be the name because it's two, so it's a CH2 pair of protons with R groups on either side of the carbon there. And this carbon would be alpha to this oxygen here, and it would be beta to, or actually alpha rather, to the carbonyl group as well. So it's alpha to an ether oxygen, and it's alpha to a carbonyl carbon or a carbonyl group. So standard methylene groups have a chemical shift of 1.2. We see that it is alpha to an ether carbon, so that adds 2.5, and it's also alpha to the carbonyl group, which is going to add 1 total. So I would expect that to have a chemical shift of 1.2 plus 2.5, 3.7, 4.7 parts per million for the signal given for that pair of protons that we have identified there. Now, this two hydrogens here, they are also alpha, so that is also a methylene group, 1.2 parts per million standard. They are also alpha to this ether oxygen. They're alpha to the ether oxygen. So that's going to add 2.5 to my chemical shift for those carbons, or those hydrogens rather. And they are beta, so that would be the beta carbon for this ester group here. That would be the beta carbon for that ester group there. So the ester has a total addition of 3 in the alpha position. In the beta position, it's going to be about a fifth of that, so it's only going to be about 0.6. So 1.2 plus 2.5 is 3.7 again, plus 0.6 in this case. I would expect a chemical shift of 4.3 parts per million for those protons. So 4.7 would be the signal for those two protons. 4.3 would be the signal for those two protons. We also have some CH3 protons here, and they are beta to this carbonyl group there, or the ester group there. So we can see that methyl carbons generally start at 0.9, but they are beta to the ester carbon there, so that's going to add 0.6 to their chemical shift. So I'm going to expect a total chemical shift of 1.5 for that set of carbons there. So I would expect 3 signals in the NMR for this molecule. I would expect one group of signals at 4.7 parts per million, one group of signals at 4.3 parts per million, and one group of signals at 1.5 parts per million. Now moving on to the second molecule that we have down here, we can see that there is a methyl set. Oh, we have to go back a slide. We can see that there is a methyl set of protons here, a methylene set of protons there, a single proton there by himself, and a couple of methyl groups there. So I would expect 4 different signals from this molecule, and starting from the left, that is a methyl group that is in the alpha position to a carbonyl group. So methyl groups have a standard chemical shift of 0.9 parts per million, plus being alpha to the carbonyl group there will add 1, so I would expect 1.9 parts per million for the chemical shift of that particular methyl group. In the case of the methylene protons that come next, we see that those typically start at 1.2 parts per million. They are also alpha to the carbonyl group, so that's going to have a +1 effect on their chemical shift. So I would expect 2.2 parts per million for that pair of methylene protons there. The so-called methane proton that we see next, they start at 1.7 parts per million, and it is beta to the carbonyl group. So 1/5 of 1 is 0.2, so I'm going to expect it to have a signal also at 1.9 parts per million. And finally, I have two methyl groups on the very end there, and those two methyl groups are not alpha nor beta to any oxygen structure, so I would expect them to have a plain 0.9 part per million chemical shift on the signal for those methyl groups. So 4 total signals in this molecule, each with the demonstrated chemical shift. So we can here on this slide, our next factor that we are going to be able to determine from an NMR signal is the integration of that signal for you calculus lovers, the area underneath the complete signal, so all of the peaks of the signal, can be correlated to the number of protons represented by that signal. The number of hydrogen atoms represented by that signal is correlated to the area underneath. Luckily, today's computers usually do all of the math for us. They'll do the area and they'll do the comparison math that needs to be done. If it's not already done for you, you can do the comparison math by dividing the area of each curve by the smallest area present. This is the ratio of protons giving rise to each signal. If one of the results has a decimal, you need to multiply everything by a small integer to get rid of the decimal. And you have to be careful, these are relative. So when you have these high symmetry situations, you can get relative numbers that need to be adjusted. So we can see some of the examples here in the slide that we have. Bring up the laser pointer. So we can see this one bromopropane molecule here has 3 different peaks, and we know that we just know from our structural knowledge now that there would be 2 protons here, 2 protons here, and 3 protons here. And we can see from the signals, and furthermore, as we've learned from about NMR up to this point, we would expect maybe the 2 closest to the bromines to be furthest downfield, the 1 in the middle or the 2 in the middle to be in the middle of the spectra, and the methyl protons at the end to be furthest upfield. And that is what we find here. And if we check the integration, we see that the integration, the NMRM integration, does it automatically for us. The relative area under this curve is 2, the relative area under this curve is 2, and the relative area under this curve is 3, which is what we would expect, 3, 2, and 2. Now, I have an example of the difference in, or what you have to be careful for a highly symmetric molecule here in this example. So we see in 3-pentanone, we only get 2 signals, even though there are 4 groups of protons. There are 2 pairs of equivalent proton groups in here. So we only get 2 signals, and this is an older school spectrum that doesn't have the integration already normalized for you. So you would need to normalize these integration values yourself. So what you would do is you would divide each of those by the smaller one, which is 32.5. And if we divide 32.5 by 32.5, we see the result is 1. And if we divide 48 divided by 32.5, then we get 1.5. So if we multiply 1 and 1.5 by 2 respectively, we get 2 and 3. So that makes sense. We would expect we would expect signals to have 2 and counts of 2 and 3. But in this case, the counts are 4 and 6. So that's where we have to be careful, because these integrals only give us the lowest ratio of signals of protons in these molecules. They don't give us actual numbers. It's almost like an empirical count of protons in the molecule, not a chemical formula count of protons in the molecule. So just be cognizant of that, and you'll be and it's easy to figure out how many protons each signal represents by taking into account its integration. We have some more examples of evaluating the integration here on this slide. So with the examples that you see here, the way you would approach this, like I said, these are some of the more older school examples where you have to do the evaluation yourself given the relative integration values. So we'll take the values that we see there and divide by the lowest number that we have. So for each of these, I would take these examples here, and in the first set, I see that the smallest integration value is 33.2, so I'll divide all of those by 33.2. And what I would find is this is equal to 1, this is equal to 1.5, this is equal to 1, and this one is equal to 1.5. And I can't have half of a proton in a molecule, so I need to find an integer to multiply those all by to get whole numbers. And of course that would be 2. And if I multiply everything by 2, then that becomes 2, that becomes 3, that of course becomes 2, and the final one becomes 3 as well. So what that tells me is the signal here represents 3 protons, the signal here represents 2 protons, this signal represents 3 protons, and this signal represents 2 protons. So going down to the next one, I see that the smallest number there is 18.92. And if I multiply those all by 18.92, they're all going to give me close to 1 as the result. So I'm going to assume that each of these signals is representative of 1 proton. So here we have our final characteristic of the NMR signal that we are going to learn about, and that is the splitting pattern, or the multiplicity of the signal. Undoubtedly, you've seen as we've evaluated these spectrum this far that the signals themselves are split into segmented peaks. This happens because neighboring protons can affect each other. Depending on whether one neighboring proton is aligned with or against the magnetic field, that can change the absorption of a neighboring proton to be a little bit less or a little bit more absorptive of a certain signal. So depending on the number of neighbors, chemically equivalent neighbors that a proton has, will determine the multiplicity of the signal. And we'll look at the different consequences of that going forward. So we can see an example here. We're taking into account the signal of HA. So HA is obviously highlighted here in red, and we would consider, they don't have it drawn in very well, so I'm going to draw this in. The rest of these, what we're seeing here, the rest of these are R groups, and they don't necessarily have to be the same R group, but the rest of these are R groups. So the proton HA only has 2 other proton neighbors, and you can see that those 2 other proton neighbors would be chemically equivalent as well. And because the proton HA has 2 different chemically equivalent neighbors, he's got 3 different orientations that he could find himself in. And because of that, HA is going to appear, as we say, as a triplet. So depending on how many chemically equivalent neighbors a proton has is going to determine what the splitting pattern of that proton signal is. As we said, going forward, we'll look at a couple more examples to get you um, uh, caught up to this, to get you comfortable with predicting the number of splitting in a peak for a proton. Here we have another example. We have a scenario where the proton in red has three neighbors, and so we expect the proton in red signal to be split into a quartet. So you can see a little bit of a pattern forming here. We'll talk about that on the next slide. It's important to note that in this scenario, again, maybe it'd be better if we went ahead and wrote these out. We have R's here. So there are no hydrogens in those positions there. So that means each of the HB protons, they would give one signal as well. They're all chemically equivalent. So we would only see one signal from those three protons. Those three protons have one chemically equivalent neighbor. So they would give us a doublet as their one signal would be split into two peaks. Since they have the one neighbor, we would see a doublet peak from that set of protons. So as I said on the previous slide, you can start to see a pattern arise from the number of neighbors to the splitting of the peak. And we can see here the number of equivalent protons on adjacent carbons will split a signal into n plus 1 peaks, where n is the number of equivalent protons on adjacent carbons. And so you can kind of see when we have different numbers of neighbors, how many different peaks that we will see, and the relative intensities of those peaks are given as well. So generally you kind of see a rise and then a fall. It's a little bit of a triangle to the intensity of these peaks. So when considering the multiplicity of a signal, remember three key things. Equivalent protons don't split each other. So protons all of the same group giving the same signal don't cause any splitting for one another. To split each other, protons must be within 2 or 3 bonds distance. So they can be on the same carbon or they can be on adjacent carbons to cause splitting. And the n plus 1 rule only applies to protons that are all equivalent. And we'll see what that means for non-equivalent protons coming up next. So here we see what happens when we have so-called complex splitting. What happens if a proton has two different kinds of neighbors? And we see that exact scenario here. We're looking at the signal for the HB protons, and the HB protons in this case, we can see the HB protons are here, and the HB protons have two sets of neighbors. They have the HA protons that are all chemically equivalent to one another, and they have the HC protons that are also all chemically equivalent to one another. So what that means is we could have two scenarios depending on the specifics of the signal. You have a complex splitting pattern where you have the signal for the HB wants to be split into a triplet because of the two C neighbors, but it also wants to be split into a quartet because of the three A neighbors. And depending on the strength of the instrument, a really, really nice instrument would give you all of the splitting, and we sometimes would see a quartet of triplets. So it's split into 4 because of the HAs, but each of the 4 is split into 3 because of the HCs. And it might be, but on a less nice instrument where the resolution isn't as nice, we probably would just see a multiplet, which is just a nice name for a noisy jumbled set of peaks. So just a kind of a jumble of peaks. This is where having the bigger magnet comes in handy. We get a better resolution and nicer peaks when we have more powerful instruments. So we'll either get a nice quartet of triplets, or perhaps a triplet of quartets, depending on the specifics of the molecule, or a multiplet if it's particularly noisy.